Okay, welcome everyone to our continuation of the California Fire Science series. Thank you so much everyone for being here today. We are very happy to host Professor Guillermo Rein from Imperial College London joining us. That's one of the great advantages of having this online is to get some of our guests from around. But Guillermo is actually not a stranger to California and the Bay Area. He received his PhD here at the University of California, Berkeley in mechanical engineering. And so there's some history to California wildfire science. And so Professor Rein is a professor of fire science at the Department of Mechanical Engineering at Imperial College London. He's received numerous awards in fire science and wildland fire, and his work has been recognized internationally. Most important to the work here, of course, is his contributions to smoldering fires, where he's been sort of a leading voice of haze events and smoldering fires, both in the physics and impacts. And so we're very happy to host him here today. And also showing up under my name in the background is Professor Fernandez-Bello, who is actually Professor Rein's PhD advisor and is joining us on the panel today. So I'm very glad that you were able to accept our invitation to present and looking forward to your talk.
Excellent. Thank you. Thank you so much, Michael, Stacy, and Carlos. Before I start with the technical content, I just want to say three things. One is that I really wish I was there in California with you. I absolutely love California, and haven't been there in almost 7 years. So I'm due 2 trips back soon. The second one is that is an honor and it's humbling, and I have to be careful of what I say because Carlos is there, and he is my professional father, and he taught me 95% of the things that I know about smoldering. And the last one is that it's night time here, and the family is sleeping, and I am at home. So you might see that I lower my voice so I don't wake them up. So today I would like to talk to you about smoldering combustion. I'll be telling you what it is a little bit, why it's important, and the things that we have found about how it ignites, spreads, and emits gases. I like using this photo. It's from a 2018 California fire because it shows a lot of smoldering processes taking place in the photo. I'll be discussing this during the talk. Obviously, this talk is based on the work that I've been doing with a multiple number of people, especially Carlos and my group here in Imperial College, Haze Lab. And it's just an overview of the things that we have written already. I want to start with a North American fire. This is what happened in 2008 in North Carolina. It's called the Evans fire. And it happened during the worst drought in record in the state. And it remains the largest fire they had had. At that time, it was absolute record-breaking, and I think it still remains record-breaking. The image that you see there on the left is a satellite image of the fire. The plume of the smoke is not particularly large. In California, you see plumes much larger than this, but that plume was there for 2 to 3 months. This was a flaming fire that ignited the soil, the peatlands of North Carolina, and it took an immense titanic effort to suppress. It is one of the rare cases where firefighters can claim that they have suppressed actively a smoldering fire. It happens very rarely. These are very difficult fires to suppress. But in the United States, delivering $20 million in cost of firefighting, reflooding the wetlands, the coastal wetlands of North Carolina, and also by excavating the field, they managed to stop it. 2 things that happened is that it had an absolutely immense amount of emissions. There was about a meter of soil that was burned, and it became part of the atmosphere. So the carbon emissions and the ecosystem damage was massive. And the second one is that there was an EPA headquarters next to it. And EPA is very well known for being good at analyzing gases. So they have this really nice set of experiments, this very nice set of field measurements of emissions coming from this fire, just because they could literally not avoid from the apparatus to collect samples. And they didn't look for it. It just happened next to the EPA headquarters. This was just a North American case, maybe not very well known. There are other cases. This one was very important. It was a paper in Nature. It was an satellite image of the 1997 fires in Borneo. The fires were so large, burning for 2 months during the dry season in the Southeast Asia, that the cloud of smoke reached China and Australia. And it was the first time that there was a transcontinental complaint about emissions from one continent and one country to another. And it led to agreements at the policy level between governments in Southeast Asia of what to do next time this phenomenon happens, where the fires in one country has such dramatic effects in the other ones. And since then, this policy has been taken into account. These just are examples. You can go back in time. Going back in time, I've seen Siberian fires that were smoldering in St. Petersburg in 1999, in Moscow in 1972. Indonesia obviously is there, Malaysia, and in the United States as well with some frequency. So these fires happen not often, but at the planetary scale happen quite often. Not often in a local location, in one single location. Maybe you would have one every 10 years, but at planetary scale, they happen every single year. Sometimes they are so large that they reach the news. Sometimes they're not too large and they don't reach the news. When we put them all together and we take into account the very large number of, the very large amount of emissions that they release, we're talking about something between 10 to 15% of the anthropogenic emissions, the equivalent to that percentage, and is still not accounted by IPCC, mostly because IPCC doesn't know how to take into account these type of fires when the soil is burning. The main culprit is peat. Peat is a type of soil that is rich in carbon, very rich in carbon, more than 10%. That presence of carbon makes it flammable because it's a soil, is porous, it's a thermally thick sample that upon heating produces a char. That means that it's not good in burning with a flame. It burns smoldering. It burns without a flame. That's the topic of today. More recently, there's this phenomenon happening in the last decade where we are seeing strange fires happening in the Arctic. These fires have very little observations from up close, what is called ground truth. Most of these fires have been observed from the satellite, and their behavior is very strange. It's very strange because they don't have a strong infrared signature in the Arctic, in the satellite, until they become very large. And they move very, very slowly, and they stay in the same spot burning for a very long time. These are typical characteristics of smoldering. So the few people who have been able to get closer to these fires, they have seen that there are very small flames that are spreading in the typical grasses and brushes of the Arctic. But what they leave behind is that the soil, the soil of the Arctic, that typically is frozen as permafrost, actually has started to burn. And these fires can last for a very long time and burn some depth into the permafrost, which is supposed to be protected by low temperatures. But the higher temperatures that we are seeing sometimes in the Arctic means that they've become flammable. Related to these and also to smoldering is the phenomena is called zombie fires. The zombie fires, which I love the name, is not a scientific name, but it works tremendously well to convey complex physical scientific concepts of the smoldering, for example. This is when we know there is a flaming fire, the satellite can pick it up. Maybe some people have been able to observe the plume of the flames, but because it is suppressed, rarely in the Arctic suppressed really, but what it stops because it has come the cold season. So after the suppression of the cold season, we're in the winter, the flames have disappeared, but the soil, the permafrost has started to burn. And what happens is that the fire goes inside the soil, smoldering, very slow burning, a very weak form of smoldering, but it's still being sustained. It can even snow on top of it. And below, we can still observe smoldering happening. The smoldering, when the spring arrives, starts to grow and is able to reignite the surface vegetation. And then the satellites can see these fires again with flames. And the interesting thing is that what they can see is that the flames are appearing at the end of the spring in the same location where they were at the end of the summer of the previous year. So the satellites, by correlating location in different times of a previous wildfire, they can actually see that a fire that they thought it was dead has come alive. That's zombie fires, which is a smoldering phenomena, which to most people, our experience with fire is with flames, So when we see the prevalence and the consistency of smoldering, we find that is exotic, but actually we have seen that nature really likes smoldering. It's not just about peat fires in the Arctic or in the boreal forest or in the tropics. It's also, for example, what is called residual burning. The residual burning is the transition from flaming to smoldering. So after the wildfire has spread at high speed, large flames of the bushes and the trees and burning the vegetation. And these are very scary fires that are spread at some significant speed. But what happens is that the fuel that is left behind, typically thick fuels, could be the thicker branches, the trunk, the logs, and the soil itself, or the duff layer. These are thick fuels, thermally thick. They need more time to burn. They start to smolder very typically for a very long time. It can actually be several days. The studies that have taken a look into what happens in the residual burning, when this is observed, when this is studied, they have consistently seen that most of the emissions from a wildfire globally actually come from the residual burning phase, from the smoldering one, because it happens at low speed. So the power of the heat release rate is low, but because they burn for 3 days as opposed to 20 minutes, they can release and consume a very large amount of fuel. We also have firebrands, an absolutely fascinating and very scary phenomena with their embers, storms and showers. And that is the ember itself. Most of the time, it can have a flame, but most of the time it's actually smoldering. And when it actually lands on another fuel, if it ignites it, very often it's also through smoldering and then transition to flaming. So there is a lot of smoldering and the transition to flaming in embers as well. So getting closer a little bit to the residual burning, what happens is when you have the flames, is that the flames are burning the vegetation and they are actually leaving behind the thick fuels converted into char. So flaming doesn't burn much of the char, but it generates the char. And it releases gases of course, carbon dioxide, water, typical pollutants that we see in smoke from flaming fires, but it also produces soot, which is a fascinating type of components. It's very small, it's PM 2.5 or even smaller, very carbonious black particle. What we see in the smoldering phase that happens after the flames have passed is that they actually tend to burn the char that have been produced by the flaming. So smoldering can produce char, but it actually burns char netly. I will show you, can show you that later on in experiments that we have done, and it produces char, produces ash. And it leaves, so it receives the black that the flames have left, and it leaves the gray and the white of the ash. And the smoke that it produces is completely different. It has a much larger proportion of CO, of carbon monoxide to carbon dioxide. It's a very incomplete type of combustion. It doesn't have soot. The temperatures are not high enough to produce soot in the smoldering. So we worry about other types of pollutants, for example, PAH, particle matter are quite abundant in the smoldering. Regarding the other smoldering phenomena that we mentioned, the embers, this is a beautiful paper. Carlos has many papers. The group at Berkeley has many papers on embers and in particle ignition, but I'm just highlighting this one from 2017, where they had particles of different materials. They were landing on a fuel bed, a cellulosic fuel bed under controlled conditions, and they were controlling the size of the ember, of the particle, and this temperature, and then they were getting these beautiful curves where, depending on the temperature of the ember and the size of the ember, they were seeing two types of curves. Those two curves are giving you the ignition. The one at the bottom that is easier to ignite, the temperature of the ember is lower and the size of the ember is smaller. These are smoldering ignition, is SI, smoldering ignition. And the one at the top, the one that is still possible but harder to obtain, which is a higher temperatures of the ember and bigger embers, these are smoldering, sorry, these are flaming ignition. So that's just to show how these experiments show that it's easier to initiate a smoldering than it is to produce a flaming for a fuel that has the ability to do both smoldering and flaming. But what is at the larger scale, not at the smaller scale, what are the differences between flaming and smoldering? So here to the left, you have the typical vegetation burning with flames, and the plume, the typical plume that has darker color. The plume is very buoyant because the flames are at high temperature. We're talking about 1,000 to 1,600 Celsius. So the smoke remains quite hot. And actually it can go upwards under the presence of gravity because of buoyancy, and actually it can go really high up into the atmosphere, leaving the emissions up there, and then they will travel around the continental scale and drop and dilute somewhere else. Whereas what happens in smoldering is quite different. What happens is it's not the vegetation that is burning, it's the soil itself on its peatlands, for example. It has a volumetric component going in depth that doesn't exist in flaming. We claim the smoldering are three-dimensional or volumetric fires. And the smoke they produce has a completely different color because the lack of soot and the presence of a lot of particle matter, it has more of a whitish yellowish color. And it is diluted because it's everywhere. It's not buoyant enough to be lifted up into the atmosphere. It just stays attached to the ground because it loses buoyancy. And it means that it's at the mercy of the winds to go left, right, north, or west. And it actually is where people breathe. It is where people and animals are, and impairs visibility and creates a lot of health issues, as we know, for example, in cases that has happened in Siberia or in Southeast Asia. The smoldering has many peculiarities in its physics and chemistry. All to combine, it produces two striking outcomes. One is that, as I mentioned before, it's easier to ignite smoldering than it is to initiate flaming. So for example, if we measure this into the heat flux, the amount of heat that is required to ignite smoldering, we see that we need lower heat fluxes, 8 versus 15 kilowatts per meter square for the same fuel, for example. Or actually smoldering is even possible at ambient temperatures without an ignition source. This is the process of self-heating. Self-heating ignition is a process that ends up into a smoldering hotspot. So this is the easiest type of combustion to initiate. And when we look into suppression, we see that smoldering is more difficult to suppress. It requires a much larger amount of water. If we are trying to suppress this with water, if we are trying to suppress by lowering concentration of oxygen, which we can do this in the lab, or for example, in libraries, is a way of suppression. We need to lower the concentration of oxygen significantly lower, which means that the chemistry is more consistent, not more consistent, more persistent. And if we were to try to remove the oxygen for some time, which is, for example, how mine fires in mines are suppressed, we need to keep low concentration of oxygen for months, as opposed to just minutes to suppress a flame. So this combination of being easier to ignite, but more difficult to suppress, it means that smoldering is the most persistent type of fire on Earth. So there is something about smoldering that the planet Earth finds it frequent in it. No surprise, given that these fires are easier to start and difficult to stop, that the oldest continuously burning fire on Earth, it is believed to be a coal mine that is smoldering in Australia, close to Sydney. It is actually called the Burning Mountain, and it's been burning for at least 6,000 years. Some people say that maybe actually even more than 6,000 years, maybe 200,000 years. And it's a national park. So I invite you to go there. It is not dangerous. At least it was not dangerous when I was there 4 years ago. And it's fascinating. If you are interested in smoldering combustion, it's like an amusement park for smoldering people. If you are not interested in smoldering combustion, you would need a guide to tell you the things that you are observing, because they are not very normal. When we look into the chemistry of smoldering, obviously you can imagine that as a fire scientist coming with a background in combustion, we love to spend time into this. We can explain smoldering by at least 2 steps that happen in the chemistry. We always have, both for flaming and for smoldering, we always have the pyrolysis step. The biomass being thick or thin, the wood, the needles, the peat, the ember, the wood, will always, upon being heated up, it will break down and will become a gas, which will be released into the atmosphere, a pyrolysate, and char, which remains as a solid. And pyrolysis is a process of, is endothermic, so it needs heat to be moved forward. It doesn't release any kind of heat. And then the oxidation will come in. And the oxidation is the one that will truly release heat. But now we have 2 materials that can oxidize. We have the pyrolysate, which is in the gas phase, that contains energy if it's oxidized, and the char, which is a solid and has a high carbon content and can oxidize. So depending on which of these 2 components produced by pyrolysis is oxidizing. So for example, if it's the char that is oxidizing, it would lead to smoldering, because char being a solid, the type of combustion that happens is heterogeneous, we call it, because it combines a solid with a gas and it happens on the surface of the char, and it leads to a weak type of combustion, which is a characteristic of the smoldering, consuming the char. But if it's the pyrolysate that is in the gas phase that is burning, that would lead to a flame, which is the more typical type of oxidation that we know is very high high rate of reaction and is very energetic, and it creates a flame of its own. So this is how chemistry we compare flaming and smoldering. Both of them have the pyrolysis step, but each of them are oxidizing a different product of pyrolysis. This is an experiment, how we prove in the lab. It was fun that char is being produced and consumed at the same time in the smoldering, right? So we did an experiment where we had a sample of peat. We exposed it to a really high temperature such that we can initiate the smoldering on the top, and it was burning downwards. This sample is about 20 centimeters in diameter. And you can see over there is the mass of different components as a function of time. So the black line is the mass of peat. So what happened, is the mass of peat. So you can see, sorry, it's the mass loss rate of peat. So it's the speed at which it's losing mass. So you can see that it ignites, reaches a maximum rate of mass loss, and then it continues burning, but it burns at lower temperature. And when you look into what were the components that were inside the sample at that time, now is the mass. You can see that at the beginning we had all of it was peat, but then the peat disappeared, and there was a point where there was actually no peat at all left in the sample. But what was left in the sample was the char, which will be the red line. There is a maximum amount of char that is produced precisely at the maximum amount of mass loss rate, and then the char gets consumed, and at the end it disappears. So the red line, the fact that the red line, that is the char amount, goes first up, is being produced in the pyrolysis process, and then it goes down, is being oxidized in the oxidation by smoldering process, is a scientific evidence that this is at the large sample, that this is what is happening. Obviously, in reality, what they are happening is we're talking about hundreds, if not thousands, of chemical steps at the elementary level, but at the global level, at least, the smoldering needs 2 steps. Smoldering cannot be explained by a single step. When we look at this into the lab from the top, we are seeing this is a sample of about half a meter. We ignite it on one side with a hot coil, and then we remove the coil and we just let it spread. The video is accelerated 600 times. This video took 5 hours to propagate across half a meter of peat bed. You're seeing this from the top, and you're seeing to the left the visual, and to the right you're seeing the infrared. So you can see most of the sample was consumed. So when you see these things from the top, it looks like it was just char, but in reality actually it was burning. And you can see the infrared. Can I show it to you again? You can see in the infrared how for hours the sample was hot, and it was burning in depth, although from the top we could only see a layer of char that actually at the end of the experiment it remained there because it was quenched, being exposed to the surface, and the smoldering was stronger just below that char of layer. So smoldering is low temperature. We're talking about peaks of temperature between 500 and 700, depending on the intensity. This is typical for peat. If you go, for example, into coal, you go to higher temperature for smoldering, almost 1,000. We're talking about a small amount of heat that is released per kilogram of fuel that is burning. The heat of combustion is about 1/3 of that from flaming. So smoldering is a very incomplete type of combustion. And this all results in very slow propagation rates. We're talking about millimeters per minute, as opposed to flaming, which could be actually doing meters per minute. When we look into what are the characteristics that would make a type of soil to ignite or not, the emphasis here being now peat fires, we know that obviously there are many variables. Peat is a natural fuel, is carbon stored by nature. It has a very large degree of variability. It's not the same to have lowlands than uplands, than boreal, than tropical. But when we look at this from the point of view of heat transfer expertise, we can order the variables into the most important to the less important. So for example, we know that the single most important variable is the moisture content of the peat. Peat can actually absorb a very large amount of water. When we express it in mass base, you can see that it can go above 100%. So you can have in the sample more water that you actually have soil, that you have solid. And we also see the second most important variable after moisture is the inorganic content, which is the complementary to the carbon content. So the amount of material that could burn in the sample. And what you can see here is a very famous set of experiments by Franzen in Canada in the 90s. Where these are the dots over here. So the dots are showing you the critical split between the samples that can burn, which are at the bottom, and the samples that cannot burn, which are at the top. So if you have a sample that it has a very high inorganic content, so you have a lot of sun, a lot of minerals, or is really wet, either of the two, then it would not be able to ignite. But if you have a sample that has low inorganic content, it has high carbon content, or is very dry, it can actually ignite. We repeated these experiments. We revisited the experiments of Franzen with a computer model from actually the group of Carlos from GPyro of Chris Lattenberger, and we were able to revisit and to confirm the experimental work of Franzen. Smoldering. So now I wanted to mention to you as a way of telling you what we have learned in the last 20 years working on this is 4 challenges that remain at the forefront of understanding smoldering and understanding this type of wildfires. So I'm highlighting the 4 of them now. This is the first one. The first of the challenges, fascinating for a scientist, worrisome for someone that wants to stop these fires or wants to use these fires for good, is that smoldering is multidimensional. It moves in all directions. It's volumetric. The most exotic of the components is the in-depth component, the fact that the fire can go into the soil. And actually that is the component that makes it more challenging for the satellite to understand what is happening, because from the top you will not see much movement. And it's also the one that creates the massive carbon footprint of the smoldering, because it can consume up to half a meter of the soil, which taking into account that soil has a very high density and a high density of carbon compared to vegetation fuel. That is actually what leads to the very large carbon footprint. When we look into the spread rate, the lateral and the in-depth, we see very interesting phenomena. For example, that's the spread rate as a function of moisture. And as expected, the lateral spread rate decreases with moisture. So as the soil has more moisture, the spread rate decreases, and there is a point where it has so much that it actually stops spreading. But fascinating enough, when the moisture content increases, the in-depth spread actually accelerates a little bit, in the sense that the more water it has, the smoldering is able to go deeper, slightly faster, because of the porosity, the higher porosity that a sample will have when it has more water. The water will occupy the pores, so especially when it's beyond saturation, it actually starts to swell the sample. And that means that when the water is dry, it leaves behind a char that is tremendously porous. And that actually helps the smoldering to propagate even faster with depth, which came as a surprise. When we did the experiments, we thought something was wrong. When we did the modeling, we thought something was wrong. And with Xinjiang, then we realized actually that this is not wrong, that this actually is a phenomena that we only see in the smoldering. The moisture can accelerate the spread in depth. This is also a phenomena. So the depth of burn, that example that you see over there from the 2008 Evans fire in North Carolina, the tree hanging that has lost about a meter of its soil. Obviously the tree fall down shortly after this photo. Is an in-depth component. The lateral component produces something that is also characteristic of peat fires, which is the overhang. And it's the fact that actually it likes to propagate faster, slightly faster, a little bit deeper. It doesn't like the top surface because the heat losses by the wind are too high, but it likes to be a little bit just below it. And it creates the overhang. It creates a false floor, so to speak. And then the overhang will collapse at some point because the soil will not be able to sustain such a cantilever. And it will burn strongly because it falls on the hot ash, and then the overhang creates again. So it's a cycle process, and it means that smoldering, the lateral front of the smoldering can hide under the edges of the perimeter. So that is a combination, for example, of lateral spread with a strange overhang phenomena and the depth of burn, which is quite dramatic. The second challenge that I want to talk about is a challenge that Carlos himself taught us, and it remains poorly understood, which is the transition from smoldering to flaming. That is a very famous photo from the group of Carlos at Berkeley. It's a slab of polyurethane foam. It's a porous material that chars, so it's used very often for smoldering experiments. It's been smoldering for an hour and a half, and then within a few seconds, you see the transition from a much larger type of combustion. There is a flame, and the sample is consumed much faster, 100 times faster. And that happens within fractions of a second, whereas the smoldering was happening before for hours. So smoldering is a very sudden, it's a very dramatic increase from a fire that is very slow and producing low power and low rate of emissions to suddenly a threat that is fast, powerful, and at a higher speed. The state of the art of the transition from smoldering to flaming remains very poor. We know something about flaming, we know a little bit about smoldering, and we know very little about the connection between the two of them. Oh, that's fine. Yeah. So what is important, the transition from smoldering to flaming in wildfires? Well, in wildfires, what we have is zombie fires, for example, is a phenomena where the transition from smoldering to flaming is very important. But before having to go into zombie fires and into the Arctic, the smoldering and the transition from smoldering to flaming is very well known to be an issue, for example, for firefighters. It's called rekindling. When a fire has been suppressed, the flames have been suppressed, and then days later, even weeks later, suddenly the fire starts precisely in the same spot that it had been thought to be suppressed before. And it creates dramatic situations. It requires reassessing the safety of the place and etc. So it's quite, it comes as a surprise phenomena. We still cannot understand fully the transition from smoldering to flaming. The physics and the chemistry are fascinating, although there are a few theories that little by little are getting confirmation regarding its phenomena. This is some of the experiments that Ole Miller conducted in the 90s over a layer of cellulosic powder, where he was creating a smoldering front with a leading edge and a trailing edge, and he was blowing the air in the direction of a spread, that's called forward, and he was actually also blowing the air in the opposite direction, that is called oppose, and he was able to see, for example, that's the spread rate of smoldering. You can see that no matter if you flow in oppose or forward, it is a higher velocity, there is always a higher spread, but if it's forward, the spread is much, much faster than oppose. So the sensitivity to wind is very large for forward and is lower for oppose. And then towards the very high levels of airspeed is when Ole Miller started to observe the transition to flaming. So the transition was not happening at low air velocities, but at higher velocities it started to happen. Interesting enough, in oppose mode, it was also always happening in the trailing edge of the sample, whereas in forward, it was happening sometimes in the trailing, sometimes in the leading. So forward is more energetic, faster, and the transition happens either way, leading or trailing edges, and it happens sooner, as opposed to the oppose, which is still possible, but it's not as optimal for the transition as forward. The third challenge are emissions. As I alluded to before, the emissions in smoldering are very, very different to emissions produced in smoldering, in flaming. Flaming produces everything faster. That is true. The rate of reaction is much, much faster, 100 to 1,000 times faster. But smoldering, because it's difficult to suppress and difficult to detect, can actually burn for much longer time, and ends up at the end in typical wildfires, burning more fuel than flaming. When we look into what is inside in the smoke that is produced by smoldering, the famous haze, we can unfortunately ask people in Singapore. That's a typical image of Singapore in Southeast Asia. That is the beautiful Marina Bay in a clear day, and the one at the bottom is Marina Bay in the middle of what is called haze. Haze is the cloud that I mentioned before that the smoldering fires produce. Is a cloud that stays to the ground because it's not buoyant, and it just dilutes with the wind and stays there for a very long time, for weeks. And this is the air that people in Singapore, in Southeast Asia, and in Siberia, they breathe. It's tremendously unhealthy. It has a much larger amount of carbon monoxide that we typically see in other types of smokes. It has a significant amount of particle matter of all the sizes of the 1 micron, of the 2.5, and the 10 microns. it has a significant amount of methane and ammonia and PAH. It's a very complex chemistry because it's incomplete type of combustion. It means that there is a lot of compounds, chemical compounds in it. These are some of the experiments, some of the filters that we extract from the lab when we do experiments of particle emissions. So all the way to the left, you have emissions from flaming when we force the sample to flame. It doesn't want to flame, but we can make it flame. So we can do that for a few minutes. You can see that is a much darker color. It's more, the presence of soot is abundant, especially in the large sample at the top. That's PM1 micron. It has a significant amount of soot, whereas you look into smoldering, which are the other two, towards the beginning of the ignition stage, and when it's spreading freely, there is no black, there is yellow, and you can see that there is an abundance, for example, of the largest particle matters of PM10, which is largely absent in flaming, but it's still, for example, in the spreading one, you have a significant amount of particle matter that is happening in the PM2 one. When you look into what's in the gas, I'm jumping between particle matters now, is, as I said before, obviously you have a significant amount of carbon dioxide always, or carbon monoxide and methane and ethylene. These are experiments that we have been able to find in the literature regarding boreal peat fires. And these one are experiments that we have been able to find in the literature on tropical. And you can see that being boreal or tropical, they have very similar type of emissions, but there's slightly differences. Tropical, they're always warmer and they have a bit higher content of carbon, and boreal, they're colder and they have typically less carbon. And that leads at the end when they burn into slightly different emissions. When we look into the particle matter of the boreal and the tropical, we also see that they largely agree with each other. So the physics of and the chemistry of the smoldering is more important than the differences in the ecosystem. But the ecosystems bring differences in the type of peat, and that leads to a secondary type of variation in the emissions. So we see a lot of organic carbon, particle matter. We see very little of soot, elementary carbon, and we have a significant amount of PAH, the polyaromatic hydrocarbons, which maybe would not be seen in flaming fires. And the fourth challenge, and with this I finish, is the fact that smoldering combustion and the burning in particular of soils that are rich in carbon are creating a feedback mechanism with the climate. So I'll start with the blue arrows, which are topics that I don't study, I just read them. So carbon emissions in the atmosphere are leading to climate change through the greenhouse effect. Climate change is leading to, in many places of the planet, to warmer soils and drier soils. And then we can go into the red lines, which are things that I know more about. If the soil is warmer on average and the soil is drier on average, that increases the ignition potential. Is easier to ignite a soil that is warmer and drier, and it actually even creates shortcuts for self-heating ignition that could actually even happen with warmer soils. That would lead to smoldering of peat. Peat is an ancient carbon, stored by nature. It takes between 100 to 10,000 years for nature to store this carbon. So such an oil carbon, older than 7 years, it means that immediately upon being burned, it becomes a net emission, because there is no time to grow back again the peat. So it creates a feedback mechanism, which is self-accelerating, in the sense that more smoldering fires will lead to more climate change will lead to more smoldering fires. In this case, I want to address flaming fires. I put them on the side because flaming fires could be part of this feedback mechanism, but not all flaming fires are part of this feedback mechanism. If the flaming fire is burning vegetation, needles, trees, grasses, bushes that are allowed to grow back again in the place where they have burned in less than 7 to 10 years, then the climate would not have time to adjust to the emissions, and then it becomes a neutral phenomena. The fires that are allowed to grow back again with quick vegetation become neutral phenomena, neutral emissions themselves. If the forest is not allowed to grow back again because of deforestation, or because it was a very old forest, for example, the redwoods in California, that takes more than 10 years to grow back again, then the flaming fire will also be part of this feedback mechanism of self-acceleration. So for example, fires in the boreal region are all of them also part of this feedback mechanism, because boreal forests grow very slowly. They take more than 7 years to grow, or the redwoods in California. But for example, the grasslands in Africa or or some other parts of the Mediterranean. They grow, or even in southwest of the United States, they grow back so fast, sometimes annually, that then themselves become a carbon neutral process. With this, I'm finishing my talk of today, and just that over the last 20 years, we've learned a lot, and we have a lot of fun doing experiments that take many hours and computer models that take even longer. We've been looking into smoldering forests in peatlands in the Arctic. We've been seeing fuels that is the soil itself burning, or is the residual burning of the dust layer, or the thick fuels that are left behind the flames, or even firebrand ignition. We have identified these 4 challenges that remain as challenging as they were when we started on this 20 years ago. The multidimensional spread, the fact that there is in-depth and lateral spread in the smoldering, the transition to flaming, the very complex and seriously harmful emissions that are coming from the smoldering, and the feedback to the climate change, which makes this an emerging topic. That smoldering, I'm happy to say that when I finished my PhD at Berkeley on smoldering combustion, helping Carlos work with NASA about safety in spacecraft, this was smoldering. It was not an emerging scientific topic. It was pretty much neglected, and it was denied as a scientific topic. I'm happy to fast forward 20 years and say that this is now an emerging scientific topic. It is of definitely global interest, and there is every week more people that is studying smoldering, and that makes us very happy. So with this, I finish, and I'm happy to take your questions, Mike, Stacy, and Carlos.
Thank you so much for the presentation and for being here today and sharing this all with us. So we have a question that's been submitted, and just as a reminder to those who are online with us here today, there's a Q&A button on the bottom. Please use that to submit your questions, and we'll read them out loud and share them. So the first question is from Brian McIntosh, and it's a question: what's the percentage of arsenic and other toxic substances you've measured in peat fires, both in the smoke and ash?
Good question. We have not looked into toxic components specifically. Some of them that we have found are toxic, but not specifically. For example, I've not ever looked into arsenic presence, which means that that's a field to look into. The fact that it's in complete combustion, it means that that more of complex molecules can survive the process. So it is easier, for example, to have bacteria surviving smoldering, or complex molecules like arsenic, or for example, metals, or oxide metals, metal oxide, sorry. They are also a concern in the smoke of smoldering as well. And this is the only one that we have measured. We've been looking into metals with experts in particles.
It's very interesting. You even mentioned bacteria with the metals. That's a lot of interesting things coming out. Before we get to the next question, Carlos, did you have a question you wanted to ask since you're on live?
No, actually, I have a comment related to this issue of the metals. Years ago, I was actually in the UK, in the moors near Manchester and Liverpool, and one of the concerns was that through the years, to the industrial development in the UK, the moors have slowly, they have keep growing, and there is the concern that there is a lot of metal particles and toxic components trapped in the vegetation, and that as with the climate change is becoming drier and drier. So there is the potential that if there is a smolder fire in those moors, that many of those metals would be released, or could be released, or will be released. And one of the concerns is that you have all these large communities, Liverpool, Manchester, that surrounding the moors, and that there are millions of people that they could be exposed to this component. So indeed, there is the issue of the toxic and metals trapped in the pits and on another smoldering or other vegetation that a smolder fire could trigger. And as you mentioned in your talk, in a smolder fire, there is not a large plume that will bring all those materials up and dilute them. It will keep them close to the ground. So it's a concern. That's only.
It remains a concern, Carlos. There's been a lot of questions about the topic. The question that you said about the metals that were released in the ancient, well, the industrial sites near moorlands near industrial sites, but very few studies. It's one of these topics that people want to know, but no one is doing it. There is one researcher, Gareth, in Manchester, but the point that we have with that, Carlos, is he's well-intentioned, but he doesn't know how to replicate smoldering in the lab. So he's capturing something. We just don't know what he's capturing. And then when we do smoldering very well, but we don't know what to do with the metals, nor how to handle the metals. So we're trying to work together to make sure that the two sets of expertise really are the interface between metals and smoldering. And as we speak, we might be able to have a paper on this very soon.
That's great. It's a really, always with wildfire, a multidisciplinary problem. And so I want to combine the next question. There's from Bob Yokelson, Priya Garg, and Hadi Hajalu. They all asked about smoldering to flaming transition. And it was mentioned that we know wind is obviously a factor, but there was sort of a question of what do we know about that transition, and are there any analytical or numerical models for that?
There is no theory, there is no analytical theory that can be used. There is conceptual theory. There is mostly one of them by Carlos Fernandez-Pello and his group of the role of secondary char oxidation. There is a computer model by Carlos Fernandez-Pello's group that is able to predict the transition from smoldering to flaming. And I don't know of anyone else that has even tried to simulate it. And for the specific field of wildfires, we remain very ill-equipped. So I'm very happy that all the names that you mentioned, Michael, are big figures in our field, that they have a question about transition to flaming, because we have it. I have it for 20 years. Carlos had it for 40 years. And maybe all together can actually, we don't have to wait another 40 years to get the answers.
And I think it was added while we were doing is that there's, a relationship not just with wind, but oxygen concentration, heat flux, and perhaps picking out these pieces is complex.
There are two. We did a literature review. There is a literature review we recently wrote in a paper for a special issue edited by Michael, where we review the state of the art of transition from smoldering to flaming. And when you do this, you put everything together. There are two groups in the world who have done something about this into understanding the transition. And one is Carlos. Most of the work comes from Carlos over the last 40 years. And the other one is Ole Miller from NEST. But Ole Miller stopped working on the topic in the 90s, at the end of the 90s, whereas the work of Berkeley started in the 80s and continues well until today. And these are the two only sets of experiments with models and observations and different fields that exist. As I speak, we have started finally to do experiments on the topic of the transition from smoldering to flaming. It took us a long time to start doing it. And hopefully it's a fascinating topic. I invite absolutely everyone to visit it and to chip in, to read the literature and to contribute to it. Because as Carlos was always telling us as PhD students, there is enough work for 100 scientists for 100 years here.
Just a comment, just short follow-up. Normally, we think always on the transition from smoldering to flaming, but as you pointed out today in your talk, there is the other transition, is from flaming to smoldering. So both have specific characteristics, and as I said, most of the work has been from the transition from smoldering to flaming, but actually the opposite, which is which occurs frequently in wildland fires, is also very relevant.
Yeah, indeed, the fascinating of smoldering just grows. The transition from flaming to smoldering is what people call residual burning, which I take duty on this because it seems pejorative, right? It's like, oh, it's residual, who cares, right? And this is where most of the emissions and most of the fuel are happening in transition from flaming to smoldering. And the satellite cannot see the residual burning, which is something that remote sensing people have an issue with, is that they can see the flames quite well and their satellites are optimized to see the flames. When it transitions to smoldering, the satellite goes blank.
So you mentioned that most of the emissions that come out are actually from smoldering. Here's a good anonymous question here. How do you know that? How is that determined?
Well, that's a good point, actually. So you can do this when you're doing in the lab, is at every single time when is smoldering happening and you are measuring mass loss and you're capturing the emissions. So we can do this very easily in the lab. But the breakthrough papers are from 2003. I'm happy to refer the person of the question to the papers. Where they did is they observe, they stay, instead of looking into the flames for 20 minutes, they stay several days. They noted what was burning with a flame, what was smoldering and for how long, and they were taking samples and they measure not what was emitted, but the fuel that was missing. This was rarely, this has been done only like 3 or 4 times in such amount of detail. And when they put everything together, they saw that by far most of the emissions, most of the fuel that had disappeared was actually burned in the residual phase, not in the flaming phase.
That's great information. So I'm going to combine a question from Jun Wang and Kathleen Roche, who are asking how we suppress and fight these fires. Do we only focus on the flaming part? What do we do with smoldering? And Kathleen mentioned wet sand and how to, if that's a component.
Yeah, so these fires, the smoldering fires, peat fires, are a real monster. No, we discuss typically with flaming fires that they could have a role, right? There is such a concept of the fire regime, the natural fire regime, the forest, the ecosystem, that it needs sometimes some fire or some intensity with some return interval. With smoldering, no one can think of anything good that nature has for smoldering. Although we know that nature has brings smoldering frequently, we cannot think, no one has ever been able to think of anything positive that brings to the forest, which means that is netly negative. And when it happens, we can just stop it. We can suppress it if we can, because we will not be harming the forest, the natural regime. So the first thing is to detect them. For the smoldering, you need early warning system, not just very early warning system, because it's very difficult to suppress. So you don't want the fire to go deep into the soil, and then you will have literally thousands of hotspots, and you will not be able to have enough people. You will definitely not have enough water. You will have to flat or reflat, which is what has happened in the United States, in North Carolina, or it happened 3 years ago in New Zealand. They reflat. They had to divert streams, reflat the land, increase the water table up, that it actually was above the free surface, and that would for sure stop all the hotspots. You can also wait for the wet season. This is what they do in Southeast Asia. They can try to suppress these fires in Southeast Asia, but most people know that this is just a PR show. These fires are larger than any of the helicopters and tankers that the Southeast Asia has. So they wait for the wet season in Southeast Asia. In the tropics, the wet season is really wet, and it can rain like non-stop for 2 weeks, and that will actually be equivalent to increase the water table and suppress all the fires. Or in the Arctic or in Siberia and the boreal fires, what you wait for the winter season. You wait for the snow cover, you wait for the very low temperatures that will actually quench most of the fires, exit the zombie fires.
Thank you. And there's a question now from Ethan Foote on ignition of the question disappeared in front of my eyes. Question of, there was a reference, sorry. So the question was what we know specifically about glowing firebrand ignition of building materials and buildings exposed to wildfire.
That, what Michael and Carlos know, because these are the PhD thesis on the papers that I read. So I'm going to refer the question to them.
Well, Stacy put an answer in that there was a previous talk on what we know about firebrand ignition, and I'm sharing that into the chat. And we continue to work on it, as well as NIST and IVHS and other places. But I have to be honest, we don't understand a lot about the smoldering process and the transition from smoldering to flaming, and really how that whole process works, and especially in a real wildfire scenario, there's no documentation. And so even understanding the physics to aid in our understanding would really helpful there. And I have one more question left in the Q&A from Laura Rossi, I think. The image you opened with was quite compelling. Can you speak briefly about the average distance that plumes from smoldering combustion can travel? It's interesting. I think we usually focus on flaming. So,
oh, the North Carolina fire, right? Well, is what we said before. Is the plume from smoldering is not buoyant, so it doesn't go high up. It actually you stop seeing it because it dilutes completely with the environment, and the satellite starts to stop seeing the contrast. What you see is you will have to zoom out, and then you start to see that it has become haze. And haze is a very diluted smoke that is close to the ground. I just want to mention at this point, my group at Imperial College is called Haze Lab, precisely because when I moved here, I was determined to help into this phenomena. So the plume becomes haze, and then it's more difficult to observe. And these plumes don't go high up; they don't mix with the clouds. They don't produce their own weather systems, as it happens sometimes with the flaming buoyant plumes.
Thank you so much. Well, I'll add. We have, I guess, one last question. What do you see? Because this is a question that comes from my students. We struggle to put a model to this process. It's so stochastic. Do you see hope of putting this together, or where do you see the future of smoldering combustion going in terms of research the next 10 years?
Very bright future, because there are so many questions pending, and it is so relevant that there is a bright future to smoldering combustion. I'm absolutely convinced about this. Also, you can talk to my head of the department, who can claim that I've proven to him that what I said 10 years ago, that I was going to be successful. So from the point of view of model, I guess you're referring to an analytical model. It's very difficult to come up with further analytical models. There are two analytical models. One of them is from the group of Carlos, and the other one is a model, a very basic model, is just a typical basic thermal balances. They can give you the order of magnitude. They cannot really give you much. There is a lot of work to do in analytical models. They will have to have a massive role of heat transfer and a little bit of chemistry, and it would just have to come out through a breakthrough. But so far, there is no breakthrough in analytical models, simple analytical models of smoldering. When we go into numerical models, that one we are in much better shape, because some of the models that really do deal with porous media and heat transfer and chemistry, for example, GPyro from the group of Carlos by Chris Lattenberger, that model is perfect for smoldering. Chris actually created this to be able to also handle smoldering, and my group, for example, has been working on this. We've done coal smoldering, peat smoldering, polyurethane smoldering, one-dimensional, two-dimensional, three-dimensional, and the group of Berkeley has also even done the transition to flaming. So numerically speaking, we are in better shape. And then experimental, most of the research in smoldering is still driven by experiments in the lab and observations in the field. This is still the driver. And then the models are just trying to catch up.
Yeah, I will add that one thing that is really missing is the chemical kinetics of some of these reactions. So you generally, we have used very small, very simple chemical kinetics schemes of the smolder process itself. particular, I mean, if you compare with the progress that has been made in the gas phase combustion, the pyrolysis combustion or the smoldering combustion really is in infancy.
Yeah, it is. I mean, I think the most complex chemical scheme for the spread of smoldering in biomass is 5 reactions, maybe 6. And the state of the art in the combustion of a hydrocarbon is 10,000 going upwards. So to the point that in smoldering, we don't need high performance computing. We could use it, but we don't need it. Whereas in the state of the art of flaming combustion, you need high performance computing.
So I just want to say again, thank you so much. This was really fascinating. We actually moved the whole lab group to see the talk here today.
Thank you.
And yeah, thank you again for making the time. I know it was difficult with the time zone. Please join us again next month. And also something exciting we'll start. We're going to be sending out at the end of the week sign-up form for students and early career researchers that are interested in planning and hosting this workshop for the next year, and hopefully an in-person event as well. So thank you
so
all
much
for joining us.
Thank you. Good night.